class. If it is a 2 hours class, I can take the tutorial class. So probably tomorrow or some other day for the previous topics which we have discussed. Right. I'll explain some more problems with the help of heat transfer data book. How you can do. Right. So today I'll talk about this convective heat transfer. Right. So my voice is perfect. Okay. Can anybody tell me? Yes.
Okay, sir.
Yeah. Right. So this is the convection heat transfer. So now that is a very important topic. We already talked about the basics. What we have learned, convection it is a combination of mass, momentum, and energy equations. Right. So whatever dimensional analysis, those things we have studied in fluid mechanics. But for the heat transfer problems, I have explained how to do it and how to generate an equation using the variables, different variables, and what are the repeating variables need to be taken. Right. So when you come to the convection heat transfer, there are three types mainly here. Two types. One is forced convection, another one is natural convection. These two topics will be discussed here. In forced convection, again, you have external flow and internal flow. Right. So in the external flow, basically, flat plate. This is an important thing. Right. There are cylinder. Let us say it is a solid cylinder. On this cylinder, the fluid is flowing. That also it is an external flow. Right. This is an external flow. Right. If it is a flat plate, a flat surface which we stay, generally most of the analysis will be done here. It's the flat surface. On this flat surface, the flow will be taken. Right? How the analysis we have to take. Be careful while solving these problems. I'll tell those techniques how to do it. Right. Next, coming to this internal flow. In internal flow, again, for example, it is a pipe or it is a duct. Suppose if it is a duct, I said the equivalent diameter need to be calculated for calculating Reynolds number and all. Right? If it is diametrical object, the Reynolds number is different, and what it call there is a normal flat surface that is different. While doing analysis, we'll discuss that. Right. So another thing is natural convection. Natural convection also will be discussing. Internal flow, the flow which is inside inside the system, that is internal flow post convection, and external flow post convection with the aid of some external device. The fluid is flowing over the surface, that is called as external flow. Right. So here we have to talk about the boundary layer. Right. This is for the flat plate. Keep in mind. This is the flat plate. Right. Over this flat plate, you people have studied in our fluid mechanics the boundary layer theory. But again, I talk about this boundary layer. So what is the concept of boundary layer? How the fluid varies on the surface and a flat plate, right? So again, for the cylindrical case also we study internal flow. Cylindrical case also we will have to study the boundary layer, how it varies, right? Later on I'll discuss that. So here, if the fluid is allowed to flow over a surface, this is a solid surface. This is a solid surface, flat surface. Let us say our house, in our house, a flat floor, right? So this is the leading edge. We call this as leading edge, and this one called as the trailing edge. It means where the fluid is entering, that is called as leading edge. Where the fluid is leaving, that is called as trailing edge. Right. So, for example, some quantity of fluid, let us say, some V has written, the velocity is u infinity. We take, let us say. Instead of this V, we talk our notations u infinity. Right. The free stream velocity. This is called as free stream velocity. That velocity is with u infinity, that is flowing through the surface. Right. So when it is flowing through a surface, it forms a boundary layer. It forms a boundary layer like this. So what is that boundary layer actually? That's important. So this boundary layer, it is a thickness of from this surface to and this layer thickness. This is delta. Let us assume the boundary layer thickness is nothing but delta. So keep in mind, whenever you are talking about this fluid analysis on a flat surface, you need to talk three equations. Whatever you learned in fluid mechanics, that is mass, momentum, and energy. All those three equations are mandatory. So mass and momentum you have studied in our fluid mechanics. The energy studies you will study on this heat transfer, including mass and momentum, not only the energy. Together with mass and momentum, the additional energy you have to talk here, right? So whenever the fluid is entering here, it forms a thin layer that is called as boundary layer. Right. The boundary layer is thickness. It has some thickness from this surface to this. That is, let us say delta. Right. That is delta. Right. What is this boundary layer actually? So the distance away from this surface, away from this is the solid surface. Away from this surface, this is the free stream velocity. Right? That means, as we discussed in the what it called the Newton's law of viscosity, these are the fluid particles. It has certain velocity. The velocity is small u, not u infinity. U infinity is the total velocity. The small u is the velocity of this particular fluid particle. Right. So when the boundary layer thickness, we have to define here the boundary layer thickness delta, because this is very essential here. This boundary layer, whatever we are talking, is called as hydrodynamic boundary layer thickness. That means we are talking in terms of the velocity. If you talk in terms of temperature, then that is called as the thermal boundary layer thickness. Those also we study here. Thermal boundary layer. This is important. These two are important. There is a relation between thermal boundary layer and the hydrodynamic boundary layer. Whatever boundary layer theory we have studied in our fluid mechanics, that is hydrodynamic boundary layer. The new concepts will be introduced here, that is called as thermal boundary layer. Right. So let us talk about the first the hydrodynamic boundary layer. What is this hydrodynamic boundary layer thickness? That is delta. And delta Hx. What does that x also let us talk? Right. So the distance away from the surface, where the velocity of this fluid particle is equal to free stream velocity. That thickness is called as boundary layer thickness. I repeat again, the distance, that means the distance between here to here, let us say, the distance away from this solid surface, right? So because this is, let us say, I write this as 3 meters per second. This is 3 meters per second. That is free stream velocity. But these fluid particles velocity is less than this. That means this is 0.5. This is 1.5. Like that, it is keep on increasing towards this, and it is reaching to this velocity. Right. The thickness, that means the distance at which this fluid particle velocity gets equal to this free stream velocity, that is called as boundary layer thickness. Throughout the thickness, it forms a layer that is called a boundary layer. Right. So this is about the definition of the boundary layer thickness. Anyway, we have to study here the three things. Already you have gone through it: energy, momentum, displacement thickness, momentum thickness, and energy thickness. All those things need to be studied, because in the fluid flow we have to study all these three things: mass, momentum, and energy. The mass and momentum I have studied already. That is the prior knowledge. The only thing is the energy in terms of temperature and heat transfer need to be studied. Right. Next, we have to talk in terms of the boundary layer, whether it is laminar boundary layer or torque turbulent boundary layer. Right. So in flat plate, keep in mind I am talking about only flat plate, not other geometry. Right. So in laminar boundary layer, what is turbulent boundary layer? That means in the laminar zone, if you see here, right, the fluid particles will flow in disciplined way. There is a systematic flow. See here, the fluid particles. Right. So the transition zone is nothing but slowly the fluid particles turns. There is no systematic way. right? That we can predict that these fluid particles are turning in a particular direction, right? It may predict in this direction, it may rotate in this direction, or it may rotate in this direction, but we can predict at least. But when you come to region turbulent region, the fluid particles cannot be predicted because there is a zigzag way. As I said, when you open your tap in a kitchen or at your sink, right? If you open slowly, the water particles will be in uniform manner, right? So if you open fastly, it will be converting into, it will be sprinkles like this, right? So so during this process, the change of laminar to turbulent zone, that is called as the transition zone. That is called as transition zone. This is safe zone only. This is dangerous zone. But all thermodynamic systems has to work in turbulent flows only, turbulent conditions. Turbulent gives you very efficient results in a closed system, not in the open system. For example, uh, I don't know whether it is right example or not, but in the Himachal Pradesh, few years back, many people have died below the dam. Right? When the fluid, when they opened the dam, the fluid particles were slowly, it was moving. Right? The people felt that that is not a big issue. But when it was converted into the turbulent zone, it became a transition phase. It became transition. Right? At that time, the people were trying to come out. They could able to know that it was being a force flow. That means uncontrolled flow. If there is uncontrolled flow, what happens? Definitely, the people cannot sustain there because that is an open system. In open system, there is disadvantages, but in closed system, for example, if you take an IC engine, you will talk about the turbulence. Turbulence means you have to create it. It means it mixes the air and fuel properly. Right? When it mixes, that means the premixed homogeneous mixture. If you give the small spark, it burns. Right? So always we cannot say that the turbulent is good. Right? In an open system, turbulent is disadvantages, and in closed system, turbulent could give the good efficiency. Right? So here, if we see, so this is the laminar region and transition region, turbulent region. Right? So here it forms a continuous, slowly a small layer. So it was given here. So from the laminar to turbulent. From laminar to turbulent, it is like this. It forms actually. Right. So this layer is called as the laminar sublayer. This layer is called as laminar sublayer. This is the velocity profile at the laminar zone, and this is the velocity profile at the turbulent zone. Right. So this delta is called as the boundary layer thickness. This is the total boundary layer thickness, whether it is turbulent boundary layer thickness or laminar boundary layer thickness. That depends upon the flow. Right. Problems may be pure laminar. The problems may be given up to here only. Throughout the length, the laminar problem. Right. Leదంటే the turbulent problem. It could be turbulent problem, or it could be combination of these two. For these all cases, the equations are there in data book. Right. So what our intention here? You need to find out the Reynolds number. Based on the Reynolds number, that is called as critical Reynolds number. Right? For example, I take a plate with certain distance like this, right? It has the length L, the length is L, right? So this is the fluid which is entering over this plate. This is the leading edge, I said, and this is the trailing edge. For example, I want to calculate this is the boundary layer thickness. Thickness is varying like this. I want to calculate a boundary layer thickness at a particular distance from the leading edge. Let us say at a distance x. The boundary layer, what is the boundary layer thickness? At this particular distance, what is boundary layer thickness? At this particular distance, what is boundary layer thickness? Right. So like that, we have to like that. we have to estimate this boundary layer thickness, right? So what is this critical boundary layer thickness? Critical boundary layer, boundary layer thickness means at Reynolds number Re critical. This Re critical is equal to 5 into 10 to the power of 5. 5 into 10 to the power of 5 is nothing but the critical Reynolds number for the flat plate, right? If this Reynolds number, is less than 5 into 10 to the power of 5, that is laminar flow. If it is more than 5 into 10 to the power of 5, that is called as the turbulent flow. First of all, when the problem is given, we have to check the Reynolds number. After that, checking the Reynolds number, we need to go for the whether the flow condition is a laminar flow or a turbulent flow. That is the first step of the problem while doing heat transfer problem also, right? So this is not new. The 5 into 10 to the power of 5 already we studied in the fluid mechanics. Just I'm reminding and explaining, not reminding, just explaining it. Right? So the critical Reynolds number is essential. Or Reynolds number we can know. For flat plate, the Reynolds number is equal to rho v. V is nothing but u infinity. I can take u infinity. This is u infinity, free stream velocity. Right? Rho v L. L is nothing but the thickness of this plate, as I explained with some rough figure. This is the L, the thickness of the plate. Right? Rho u infinity L divided by mu. Rho is the density of this fluid, whatever flowing over here. It can be air, it can be liquid, it can be any liquid. Right? Mu is the viscosity. These are the Reynolds. This is the Reynolds number formula. Very interestingly, many people don't know what is the Reynolds number also. That is the famous formula which we study. Right. So based on that, we can decide whether the problem is laminar or turbulent. Then the problem over, not over, because we need to go for the further steps. Before giving the heat transfer convection problem, if it is a flat plate or internal flow also, don't bother about the what we call natural convection. I'll discuss what is the condition also. Whether it is internal flow or external flow, we have the Reynolds number is essential. I'm talking about the external flow now. I'm talking about the external flat plate, right? So here you're supposed to calculate Reynolds number based on the Reynolds number, and then we have to move forward for the further solution, right? So this is the laminar and turbulent velocity profiles, which we have seen here, but elaborately it has been just elaborate depiction of this. And these are the things which we have studied: the displacement thickness, momentum thickness, and energy thickness. Displacement thickness, momentum thickness, energy thickness, based on the mass, momentum, and energy. Right. When the velocity profile is given, we can, for example, this is the surface. In this surface, the fluid is flowing. This is the velocity, u infinity. I don't know the u infinity value, but I know that u by u infinity velocity profile during this boundary layer. In this boundary layer, what is delta x, what is theta, what is delta e, you can study or you can derive. When the velocity profile is given, those velocity profiles also I will show. Those velocity profiles also I will show, right? So if the velocity profile is given, how to calculate? Because u by u infinity will be given in the problem, the fluid mechanics case. In this heat transfer case, it doesn't. These situations will not come again. Just for reminding and telling this, u by u infinity is given. The u by u infinity substitute here. U by u infinity substitute here. Integral u by u infinity and u by infinity. Integral between the limits 0 to delta. Right. So that you will get the theta, delta x and delta e. The theta is momentum thickness, displacement thickness, energy thickness. Right? This was done also. This was also done. So you don't do it here again. Right? I'm showing this slide to the understanding of the velocity profile, how that varies. If the velocity profile is given, then how to calculate displacement thickness, momentum thickness, and energy thickness. Next, conservation of mass. I said the conservation of mass, conservation of energy, conservation of momentum are important. Right? For example, within this boundary layer, this is the boundary layer, right? This is the boundary layer. In this boundary layer, consider a small element of that particular fluid particle, right? In the direction of x and y, to study about the mass, right? This will be the reflection of it, right? In the u direction, sorry, in the x direction, the velocity is u plus dou u by dou into dx, right? All those things we have done in fluid mechanics. I don't know whether you learned it or not, but it is part of fluid mechanics, 99.9%. Right. So this is the equation dou u by dou x plus dou v by dou y is equal to 0. If z direction is also there, dou w by dou z is equal to 0. Right. So this is the mass conservation of mass equation. Next, conservation of momentum, mass into acceleration. Right. So mass into acceleration. This equation, after deriving this, for the same element, whatever element we have considered in the fluid particular, in the effect of force. That means dynamics also have considered here, right? So after that, you get this. These are the famous equations: mass, momentum, and energy equations. Just giving reminding you whatever you have studied. Next, this is energy equation, right? Some the energy by heat and work. If there is work, let us consider that work also by mass also, right? For that particular element, the energy equation. This is the energy equation. Whenever there is temperature, and the specific heat, see thermal conductivity, these are present. This is the energy equation, right? So this is supposed to be derived, but not required for this undergraduation level. This is this derivation will be taking 2 to 3 hours. Even if you want to do in the exam, it takes 1 hour, right? So this is part of post graduation cases. Don't worry, right? Just a minute, I'm getting a call. Just a minute. Yeah, sorry. Is my voice audible now?
Yes, sir.
Yeah. So you don't bother about these big derivations. If I do this derivation also, definitely you people will uh, abuse me, because this is a long derivation. Right? It is not required also. Don't worry. Just to understand what is the energy equation, what are the terms present, right? So whenever there is a temperature and Cp and all those things, these are the mass, momentum, and energy equations. Next, the overview of this, and this is the famous equation. Anyway, these three are also famous equations, but this is the von Karman momentum equation for boundary layer flow, right? So the tau naught is nothing but shear stress, rho is density, this is u infinity, that is free stream velocity, dt by dx. With respect to dx, this theta is nothing but the momentum thickness. For this also there is a big derivation you might have done in fluid mechanics. Again, you don't need to do here. Like, and then how to get it? How to the drag force we have to get it, right? How to the skin friction coefficients we have to get, right? Drag and lift we study in our aerodynamics. Right? The fluid flow is very important together with the energy. Right? So this theta is nothing but momentum thickness. Right? Substitute that momentum thickness 0 to delta, 0 to delta u by u infinity into 1 minus u by u infinity into dy. Right? In place of u by infinity, using this equation we have to solve with the help of the boundary conditions. Those boundary conditions will also be given in the problem. Might have given. Already it is done. Right? So substitute in place of u by u infinity, right? The given velocity profile. Then solve this using, you'll get the drag, shear stress, skin friction coefficient, all things you'll get with the help of this. Right? See, this is the case. For example, if the velocity profile is given like this, the boundary conditions are given like this, after doing with the help of this previous shown the von Karman integral equation, you have to get the boundary layer thickness. This is boundary layer thickness like this, and this is CF, that is skin friction coefficient. You have to get like this. Rex is nothing but Reynolds number at a particular distance. For example, this is the plate. The throat length is L, but I am calculating the Reynolds number at a distance L. Actually, the distance is 2 meters, but I am calculating a distance 0.5 meter. That is x at a distance x. This 0.5 is the x. Right. So throughout the length, if I am calculating, then that is L according to L. If I use this profile, I will get this delta, this CF. If I use the profile like this, if they use profile with the help of sine, right? So these are the boundary conditions which you're supposed to use this boundary condition, and I get the delta values, varying delta values. This practice we supposed to do it in fluid mechanics only. Here we cannot do it because just application of that. Right. So Blasius has found the one common solution for this. Right. So almost the many velocity profiles within this range. So that based on this research, and Blasius has introduced a solution, the common solution, that is for boundary layer thickness, hydrodynamic boundary layer thickness over this for laminar flow only. This is for laminar flow. Turbulent flow, this is different. 5 into x divided by root over REX. 5x is nothing but the distance, or this is the CF, skin friction coefficient. These will be used. Right. So all these things we cannot remember. Right. Even this also cannot be remembered. So this will be given in your data. This is the Blasius solution. You're supposed to use the Blasius solution. For example, in the problem velocity profile is given like this, then definitely you must remember this. You have to remember this. Right? You have to remember this. Otherwise, it cannot be done because this is the specified profile. If he mentions that it is a Blasius exact solution, or if he doesn't mention also, then we are supposed to follow according to these equations. So 99.9% of heat phase transfer problem in your undergraduation level based on the Blasius solution. Okay. So because this equation is given in data book. Right. Now, so a simple problem with the help of the things, air is flowing over a smooth flat plate with a velocity, that is velocity is nothing but u infinity, let us say 12 meters per second. So whatever velocity is given, that is u infinity only over throughout this velocity, not a particular small velocity. Remember, and the profile is like this. The length of the blade is 1.1 meter. The blade is given like this. Right? The length of the blade is given like this. The width is also given. Over this, the fluid is allowed to flow with a velocity of 12 meters per second. If the laminar boundary layer exists up to the value of Reynolds number 2 into 10 to the power of 5, accept 5 into 10 to the power, not 2 into 100. It's wrong one. Right? And the kinematic viscosity is given in Stokes. Whenever it is given in Stokes, you're supposed to convert it into nu is equal to Stokes. Right? Stokes in new meter square per second can convert here. Right? You are supposed to multiply 10 to the power of minus 4. Conversion, you must know the conversion from Stokes to Newton meter square per second. Right? So, after that, what is asking you to calculate? What is the maximum distance of leading edge up to which laminar exists? The maximum thickness of the boundary layer. These things is asking you to calculate. Right. So, assume this is 2 into 5, 10 to the power of 500. Whatever value has given, let us follow with that. Right. So, this is the problem. We come to the solution. This is the way. Right. So, he has given the velocity profile. And he is asking you to calculate the boundary layer thickness. At what distance, this is the critical Reynolds number according to his case. Right? But at what distance he is asking? This critical Reynolds number, for example, this is flowed the L, this is the L actually. Length of the flare, the fluid is flowing, this total is 1.1. And he has given some critical Reynolds number 2 into 10 to the power of 5. Where this 2 into 10 to the power of 5 exists, that is R critical X. R critical X. Right. So Rx is given directly 2 into 10 to the power of 5, but our formula is u into x divided by nu. Right. So u is 12, x need to be found. That means what is the distance from here to here to exist this particular Reynolds number? Right. 0.5 into 10 to the power of minus 4. Unless you convert, you get wrong answer. So x value will get, that is 0.25. That means the distance at this point it is 0.25. At x is equal to 0.25, what happens? This is the Reynolds number 2 into 10 to the power 5. Next, he asks you to calculate the delta. Right? Delta you need to calculate. Right? How do you calculate the delta? Can I use the Blasey solution? No, I cannot use the Blasey solution because he has mentioned the velocity profile. Right? Based on this velocity profile, I have shown in the table. This is the derived delta value. Right? This equation need to be used for calculation of delta. Right? So in place of x, whatever x you substitute here, and Reynolds x, Rex, whatever x, Rex is given, substitute, you will get the delta. Delta is nothing but thickness, so you will get in mm. Right? If మీరు చేసిన ప్రాబ్లమ్స్ నేను మళ్ళీ మీకు రిమైండర్ చేస్తున్నాను. రిమైండర్ ఇస్తున్నాను. రిమైండింగ్. Recap. One more problem. Give this, don't worry. Plate length 750 mm, width 250 mm, placed longitudinally. Stream of fluid oil is flowing. Whatever fluid, it doesn't matter whether it is air or whatever. Right? If the oil has a specific gravity like this, density, specific gravity is nothing but density, and kinematic viscosity is Stokes. You can calculate mu is equal to mu by rho. You can calculate mu. Right? How do you calculate density? Because the specific gravity is given. You know that the specific gravity is equal to density of any liquid to the density of standard liquid, water. You know, fluid mechanics you studied. That is the second property or third property of your fluid mechanics. So specific gravity into the 1000, it gives you the density of the particular fluid. This is a continuous thing. Whatever you learn, whatever basics you have learned, right? That is a continuous process. It will be applied. Right. So calculate the boundary layer thickness of the middle of the plate, shear stress of the middle of the plate, friction drying. I show you. That's all. Simply I show you. So why did I take here this equation? Because he has not mentioned the velocity profile. So I have taken the Blasius equation. Right? So according to the Blasius equation, you will get this effect CFX value. Shear stress, you know. ఇవన్నీ అందులో FM లో నేర్చుకునే half rho u infinity square. right? Based on it, you need to calculate like this. Simple, very simple. But here you have to calculate the Reynolds number. Critical Reynolds number is not given. Rho ux divided by mu or ux divided by mu. This is u into L kaadu. U L and rayachchu. If it is throughout the length, you are supposed to take L. That is the difference. If it is at a particular distance, that is x divided by mu, because mu by rho is that becomes mu. Mu is given in Stokes, 1 into 10 to the power of 4 meter square per second. So this is 18,750 laminar flow, which is less than 5 into 10 to the power of 5. That is the standard for the flat plate. Right. So that need to be calculated. At the middle of the plate, he said. At the middle of the plate means he has given the length 0.75 or 750 mm he has given, and width is given. Right. So this 0.75 half and at the middle of the plate, this x value need to be substituted in the half that. So you get the delta value. Right. After getting delta and again CFX is different 0.664. Again, మీరు worry అవ్వాల్సిన అవసరం లేదు. You need not to worry. You need not to worry because this will be available in data book. This application, so you don't need to remember. In fluid mechanics, you learn the subject, so you definitely must know this the procedure. This is the application, so it is given in data book. Every equations cannot be remembered. Right, this is the way of doing the problem. The friction drag, if you want to calculate, you can calculate the friction drag like this. This is nothing new. I'm again repeating. At the same time, I'm not focusing too much also, because it is existing knowledge to get an idea. At the same time, to recap, that need to be added here. In addition to these calculations, you are supposed to do the heat transfer. That is the extra thing here. This is thermal boundary layer, right? For flat plate, we have already discussed the hydrodynamic boundary layer. This is thermal boundary layer. That is the difference. There is no difference of it. Velocity, in the form of velocity we have studied, and in the form of thermal, the temperature or temperature variation I have to study. See the same thing. This is the laminar flow. So this was the velocity profile. Now the temperature profile is here. The temperature difference will be more. Whenever it is the velocities keep on increasing, what happens? The temperature difference it reduces. It could be a laminar flow or it could be a temperature turbulent flow. The temperature variation will be like this, right? So this can be this is the elaborated view. This is the elaborated view. That means, what is this? The thermal boundary layer thickness. Thermal boundary layer thickness, that means the distance away from the surface where the temperatures attains the free stream 99% actually. 99% of free stream velocity and 99% of free stream temperature. Not exactly equal to the free stream velocity, 99%, 0.99 times. Right? Or it could be 0 in ideal case. That is the difference. See the temperature profile T infinity, this is surface temperature. Right? At the same time, you try to do that is one of the gate question. Right? If surface temperature is more than the fluid temperature, what is the temperature profile? This is the temperature profile. If the fluid temperature is more than the surface temperature, what is the temperature profile? You try to do this. I have answer for this, but you think it out. You try to draw this, and you can somebody can tell me in the next class. Right? So this is the variation of thermal boundary layer. Again, Prandtl number. Whenever there is heat transfer, there will be Prandtl number. I said in the last class, then non-dimensional numbers I introduced while introducing this. Right? So this is the ratio of molecular diffusivity of momentum, molecular diffusivity of heat. We can write mu by rho and mu Cp by K. Don't bother about this nu here. We are using mu here for the kinematic viscosity, right? But for definition I have taken here mu Cp by K. You must remember it. You don't need to remember. While doing problem, Prandtl number also need to be calculated, but this Prandtl number directly it is given in tables. It is given directly in the tables, right? So, and this is the variation of thermal boundary layers. If it is a Prandtl number is less than 1, if this Prandtl number is less than 1, this is equal to 1, and this is for greater than 1. Right. So now you differentiate. Right. So Prandtl number is greater than 1 means the thermal boundary layer thickness is less than 1. Right. This differentiation I'll discuss again in the coming classes. Don't worry. This is the variation of thermal boundary layers. Right. For Prandtl number 1, both thermal boundary layer and hydrodynamic boundary layer will exist. Meet at the same place. Right. Prandtl number is less than 1. This will be more than this. Greater than 1. This will be more than this. That means thermal boundary layer will be more than this. Hydrodynamic boundary layer thickness. Right. In Prandtl number less than 1, thermal boundary layer thickness will be less than hydrodynamic boundary layer. Right. So like that, based on the Prandtl number, whether which will be more, thermal boundary layer will be more or hydrodynamic boundary layer will be more. Right. That information I'll provide in the next session. Don't worry. Right. So this is some problem. Right. Dear students, carefully listen to me. I will tell you how to do the problem of this convection heat transfer. Flat plate problem. First you listen. Right. I tell you the procedure now. I don't want to solve the problem now. Right. I'll tell you how to approach the problem. That's very, very important. So far, do you have any questions? Yes, any questions, students? Let me know, yes or no. Yes, dear students. 311. A0311. Do you have any questions? Yes. 340. Is my voice audible? Now voice వినిపిస్తుందా?
Yes, sir.
Yeah. Okay. If you don't have questions, I'll explain this problem. Listen very carefully, because if you listen this problem, you can do any type of problem. Right. Keep in mind that these properties will not be given in the problem. Right. So now we enter to the problem. Just whatever problem is given, what type of problem ఇప్పుడు నేను ఫ్లాట్ ప్లేట్ చెప్తున్నాను కాబట్టి ఇది ఫ్లాట్ ప్లేట్ అని చెప్పేస్తున్నాను. బట్ ఎగ్జామ్ లో ఫ్లాట్ ప్లేటా లేకపోతే ఇంటర్నల్ ఫ్లో ఎక్స్టర్నల్ ఫ్లో అది ఐడెంటిఫై చేయాలి. ఫస్ట్ ఐడెంటిఫై ద ప్రాబ్లం, వెదర్ ఇట్ ఈస్ internal flow problem or external flow problem, and what it call forced convection problem or natural convection problem that need to be identified. Right. So keep in mind very simply, forced convection అయితే velocity ఇస్తాడు, natural convection అయితే velocity. The velocities are very, very, very less, so he don't give the velocities. Right. So when the velocity is given, assume that that is a forced convection problem. That's the first step. Second step, identify whether internal flow or external flow. First, natural convection or forced convection. Internal flow or external flow. See, flowing over a flat plate, so external flow. Flowing over a flat plate, that is external flow. Next step is, what is the fluid here? That's important. The fluid తెలియకపోతే మీకు అసలు ప్రాబ్లమే తెలియదు. This fluid is air. The fluid is air. First two steps are to identify whether type of convection and type of flow, internal or external flow. Remaining steps are same for all the problems. I repeat again. First step 1, to identify whether the forced convection or natural convection. That is step 1. Step 2, whether internal flow or external flow. That is generally applicable for forced convection only. Free convection problems, that is directly on the surface. Of course, there will be some cases, but those cases not required to you. Don't worry. Third case, third case is common. What is that? Identify of the fluid. What type of fluid is flowing over the surface? That is very important. Right. At the same time, when the fluid is flowing on the surface, the fluid temperature telustundi and the surface temperature telustundi. If you know these two temperatures, calculate the mean temperature. The mean temperature is nothing but TF. The TF is nothing but T infinity plus TS plus T infinity divided by 2. Step 1, identification of natural or forced convection. Step 2, internal flow or external flow. Step 3, calculation of TF. That is mean temperature or bulk mean temperature, we call it as. That mean temperature, see here the surface temperature is 56 is given, and next 28 is air temperature, fluid temperature. Or ended in mean temperature, find out. After finding out the mean temperature, at mean temperature TF, get the properties from data book corresponding to the given fluid air. I repeat again. After calculating the TF, get the properties from data book. These properties will not be given in the problem. The very 1% chance of giving the properties, right? Nothing will be given. These things are all available in the data book, even Prandtl number also. E properties, air properties, dry air, dry air and data book. Corresponding to E temperature, TF temperature, not TS or not T infinity. At TF you have to take the properties, right? These are the common steps. Even steps, generally steps. Problem, I'm not talking this problem. I'm not talking about this problem. In general, I'm discussing the steps. After calculating the TF, you have to get the properties from data book corresponding to the particular TF and air property. Air is air, water is the water, engine oil is the engine oil, whatever it is. Air is the flow, and corresponding values is equal. Right. After taking that, you have to calculate the Reynolds number. That is important. Forced convection like the Reynolds number find out chestaru. Natural convection like the Grashof number find out chestaru. Adi malla discuss chestam. Right. If it is in the flat plate case, Reynolds number rho VL by mu. In the flat plate case. If it is a diametrical object, internal flow RED, and rho VD by mu. And it depends. If it is the length kabatti, rho VL by mu find out chestam. Or rho VL and rho U infinity L and V and velocity L. U infinity. I take this U infinity. Right? So calculate this Reynolds number. Whether the laminar turbulent conditions may different may discuss. For example, I discuss for the this case. Rho U infinity into L by mu for flat plate case. Calculate this. If it is laminar flow, go to data book. I tell you how to take the calculate all boundary thickness, local laminar flow. Turbulent flow is very equations. Right. I uses of data book. I'll discuss tomorrow. I'll discuss in tomorrow's class. Right. So whether it is turbulent flow, external flow, laminar flow, turbulent flow for flat plate, External flow వేరే సర్ఫేసెస్ కూడా ఉంటాయి. అవన్నీ చేసుకొని వీ హ్యావ్ టు గెట్ ది నసెల్ట్ నెంబర్ ఈక్వేషన్ అగైన్. ఆ నసెల్ట్ నెంబర్ ఈక్వేషన్ తెలిస్తే నాకు హెచ్ వస్తుంది. హెచ్ తీసుకెళ్లి క్యూలో సబ్స్టిట్యూట్ చేస్తే హీట్ ట్రాన్స్ఫర్ వస్తుంది. ఐ డిస్కస్ దిస్ ప్రాబ్లమ్ ఎలాబొరేట్లీ టుమారో so that you can do any type of problem, right? So I think with this I'll end because you have the training classes, right? If you have any questions, let me know, or else I will execute. Shall I end it? Shall I end?
Yes, sir.
Okay, if you don't have questions, I'll end because you said you have training, right? I'll discuss tomorrow. Okay.